That's the link. So also gonna be the lowest ever. That's the link. Man, I could go. That's the right now. That will find me a good company.
I carried my height below 70 in my class.
What? Wait, repeat everything you just said. It was all like in one ear, on the other. Acknowledgement. That's it.
Yeah.
I'd like to be great.
That's what my grade is really low.
Yeah.
There's a group.
Let's change That's great, man.
Like got like a.
You got a low score on the acknowledgement.
No, I'm not.
Yeah, I did.
But you get a low grade on that.
All right, let's talk about geometric sequence and series, guys. All right, so okay, so what is a geometric sequence? We're on page 7. Geometric sequence is one in which the same number is multiplied to each term to get to the next term in the sequence. The number you multiply is called the common ratio. Denoted by the letter R. So there are a couple of ways to build a rule for geometric sequence. It depends on which term you're starting with. If you're starting with the term before the first term, you can just divide by the ratio to get that previous term, and then do times r to the n. You can also find, if you're starting with the a sub 1, you can do times r to the n minus 1. That will get you the first term, second term, third term. So again, all these are adapted based off of where your starting point is. So we're starting at a sub 2, then it'll be times r to the n minus 2. So number 1, we have 3, 6, 12, 24, 48. We know that this is a geometric sequence if we can divide the term and the term before it and get the same ratio every time. So here, 12 divided by 6 is 2. 6 divided by 3 is 2 as well. So we know that we're multiplying by 2 every time to get to the next term. Here's the formula. If I want to find the ratio, it's for geometric sequence, it's a sub n divided by a sub n minus 1. Doesn't matter which terms you choose, as long as you choose the term before it, as long as you divide by the term before it, and that's going to get you your r. So no matter which term we choose, if we divide it by the term before it, we're always going to get 2. That's our ratio. This one feels more straightforward here. A sub n equals a sub 1. So my a sub 1 is 3. So it's 3 times 2 to the n minus 1. This formula will get me to the 3, 6, 12, 24, 48. If I were starting off at n equals 1, it'll give me that first term. Like n equals 2n, I'll give me my second term. It also works with this formula, but I do need to find the term before 3, which is, so I got to divide 3 by 2. And if I can start off with the term before it, a sub 0 times 2 to the n, that would also get me to those indicated terms. We can also start at the second term, 6 times 2 to the n minus 2. So all of these will get us the list of terms.
Why is 3 not a sub 9? Like, why do we have to put 3 into the second one? Why can't we just put the first one? Like, what makes us realize that we have to go backwards to find a sub 9? Like, why is 3 not it?
Right. So the understood rule of the sequence is that 3 is my a sub 1, not a sub 0. So just different variations. Okay, you guys want to try number 2? Find the ratio and then follow the same pattern as number 1. So my ratio is 1/5. I take the second term divided by the first term, I get 5/25, which reduces to 1/5. The one that feels easier to use is that middle one there, 25 times 1/5 to the n minus 1. But I can also divide by 1/5, get to the previous term, 125 times 1/5 to the n, or 5 times 1/5 to the n minus 2. This is just a geometric series that is written as summation in summation notation. So if I have a times r to the nth, this would be a plus a times r plus a times r squared plus dot 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 plus a times r to the n power. So every term is getting not only multiplied with the previous term, but we're also adding the previous terms to it. So we call this geometric infinite series. And the geometric series will converge if every term that comes after it is small enough, right? So the idea is that if we want to be able to add up infinite numbers of terms and be able to get to a sum that is converging, we can't have increasing numbers, right? Every number has to be smaller, but it has to be small enough where we can actually get a sum out of it. So here's the rule. A geometric series with ratio r will diverge if the absolute value of r is greater than 1. So if I'm multiplying by a ratio that's greater than 1, that is obviously going to make the next term even larger. And there's no way that I can add terms that gets larger and larger and expect a sum that will give me a real number, or infinite sum that will give me a real number. However, if my ratio if the absolute value of my ratio is between 0 and 1, then my series can converge. And my sum is actually going to come out to be this a sub 1 over 1 minus r. This is one of the few rules that allows us to not only find whether a series converge or diverge, but also find the actual sum. Most of our, we're going to learn about all these different tests for whether a series converge or diverge, but most of our tests, we're not going to be able to, or we're not going to be asked about finding the actual sum. We just have to be able to determine whether the series converge or diverge and to be able to provide appropriate justification. But if it's a geometric series that converges, you could be asked how to actually find the sum of that series. All right, any questions so far? All right, let's look at number 1. Sometimes it may not be very apparent that something is a geometric series. Sometimes we need, it helps to kind of manipulate the expression into something that fits our form a little easier. So we can pick out our a sub 1, our ratio, and to be able to, well, first determine whether a series converge or diverge, and then if asked to find the sum as well. So number 1 here, we're asked to find the sum of the series. So let's first determine whether it is a geometric series, determine whether it will converge or diverge, because if it diverges, we just can say that the sum is infinity. But if it converges, we can take the next step and actually find the number of that sum. So here, 3 over 4 to the n, maybe it helps to rewrite this as 3 times 1/4 to the n, because then it fits this form a little bit better here. All right, you have that ratio, which you want as a numeric value raised to the nth power, which is the variable here. So my ratio is equal to 1/4, and absolute value of 1/4 is still less than 1. So this indicates to us that this series converges. Now that we know that it's a geometric series that converges, we can actually find the sum. We can actually get a real number out of this process. So we're going to find a sub 1. Now, a sub 1 is the first term in this sequence. It doesn't mean that we always plug in 0. Make sure that you're always plugging in the first term in the lower bound. A lot of times it is 0, but sometimes it could be 1, it could be 2. So we got to spend the time to actually plug in. So don't assume that, oh, I'm just always going to replace n with 0. Not always the case. In this case, it is. So if I plug 0 in for n, what is my first term going to be? 3. Yeah. So my first term is 3. My ratio is 1/4. Now, when you're testing to see whether a ratio is going to converge or diverge, you want to put absolute value bars around it to make sure that it's a positive number. But when you're going through the formula, if it's a negative ratio, then you want to hold on to that negative value. Okay. So the absolute value is just for confirming whether it passes these conditions of convergence or divergence. All right, so then my sum of this infinite series is just a sub 1 divided by 1 minus r. Three divided by 3/4, the same thing as 3 times 4/3, which is 4. So we can actually add up all these infinite numbers of terms. Because the ratio is less than 1, we can actually find that the sum will get closer and closer towards 4. All right, any questions with 1? Thank you. Number 2, it may not seem apparent that it's geometric series, so it's nice to break those or use exponent properties to see if we can split up and rearrange it in a way that can help us see things a little bit more clearly. So I'm going to rewrite this as 3 to the n times 3 to the first power over 4 to the n. And if I can break it up in that way, maybe I can rearrange it a little bit more in a way that can be helpful for matching my form. So I can also write it this way, right? I can have the 3 in front and then put the 3 to the n over 4 to the n. I can write that as 3 over 4 to the n. So from here to here to here, this is a lot more clear because then this matches our geometric series a little bit more clearly. We have our obvious ratio of 3/4. We know the absolute value of 3/4 is less than 1. Our series converge, geometric series converges. And we can also find the sum because this is actually a converging series. Now, how can I find my first term? Well, good, plug in 2, right? Plug 2 into any of these terms here. So if I plug 2 in here, I'll get 3 to the 2 plus 1, which is 3 cubed over 4 squared. (27/16), so that's my a sub 1. So now we're just plugging it into our sum formula for geometric series. A sub 1 is 27/16. My ratio is 3/4. So 1 minus 3/4 is 1/4. 27/16 divided by 1/4, the same thing as 20/16 times 4/1. We get 27/4. Page 8. For what value of r does the infinite series summation of 17r to the n equal to 23? So we want a sum of 23. We can also figure out what a sub 1 is, because a sub 1 is just going to be the first term if I were to plug 0 in for n. And the nice thing is r to the 0 power is going to be 1. 1 times 17 is 17. So we know a sub 1 is 17. Let's put into our formula for our geometric series. 23 is equal to a sub 1 over 1 minus r. Just cross multiply, solve for r algebraically. Number 4, before looks a little messy, but let's start off by plugging in 7 for x, right? We can at least do that as our first step. Let's just see what that takes us. Sorry, 7 over 3. All right, so we know that this is going to be a geometric series here. I can plug 3 in to get my a sub 1. That's just calculator work there. And my ratio is just this expression, right? My ratio is this expression that is inside that n. So my ratio, I can rewrite that sine squared of 7/3 as sine of 7/3 squared, just to make it a little bit easier to plug in, since most calculators are not going to be able to write it in this exponent in this form. So we know that this is my ratio, since this is my r to the n. We find the decimal value associated with that r, and then we can use our calculator to find the sum using s equals 1, a sub 1 over 1 minus r. Because if I want to find my first term, my a sub 1 would be whatever this number is when I plug 3 into this value. So you don't have to put the 2 out here. I should put the 2 out here so that it'll be easier to plug in the calculator, because it's hard to put sine squared to the 7/3 in the calculator. So I should put that 2. And that 2 also need that 3 there, because I'm trying to find that first term when n is 3. Okay, let's do the first few problems, see how we feel about these problems, as you know, after we do these after the examples that we've done. Do these problems make sense in terms of determining your a sub 1, determining your ratio, determining if the series converge, and if the series converge, can you find the sum? Okay, so try number 1. Again, I think it helps sometimes to kind of rewrite it in that a times r to the nth form, so that you can more easily pick out what your ratio is. So sometimes the problem is written in a way that that is not as clean as it could be. So it really helps if you can rewrite your problem like this. Push that -3 to the n in the denominator as -1/3 to the n. If you can get into that form, then it's really clear what your ratio is. Find your first term. Your ratio is -1/3. You know the absolute value of -1/3 is less than 1. Eventually, we're going to have to justify the test that we're using. And this is the geometric series test. So a lot of times we'll just say, oh, this series converges by geometric series test by GST. And then because of the summation in the problem, we know we're also asked to find the sum. So then we also find the sum as well. All right, try number 2. Right, let's try 3 and 4, and then we can do some more polar area from the worksheet yesterday. So number three, we see that if we can get that exponent n to come out, then our ratio is e to the x. And we know e to the x is less than 1 because we know x, well, first off, well, e is around 2.7, but if you have 2.7 raised to a negative exponent, then it's like 1 over 2.7. And you know that ratio is definitely less than 1, so that's a safe converging series. A sub 1 is e to the 0 times x. Anything times 0 is 0. E raised to 0 is 1. So my a sub 1 is 1. And my ratio is e to the x. All I know is that e to x is less than 0. I don't know what x is. So the furthest I can go from what's given to me is the sum is 1 over 1 minus e to the x. Number 4, e over pi to the n. E is 2.7, pi is 3.14. That ratio is clearly less than 1. So my ratio is e over pi. But a sub 1 is also e over pi because if I would plug n in for 1 and for n, I get e over pi. So then we should follow our formula, e over pi over 1 minus the ratio. Common denominator, do some cleanup, multiply by the reciprocal, and I get it cleaned up to be e over pi minus e. Okay, your homework is pages 5 through 10 to finish off the AP problems from the previous section, and then to make some progress with the geometric series practice problems. I'll send out a reminder on Sunday about these pages. Let's go to our polar area worksheet. And I want us to try 37 and 38 on the third page of your worksheet there. So polar area worksheet. I just completed the key and I posted it on my website. So I'll also send a link to the key over the weekend. But I think I put it under yesterday's date, worksheet and the key. So what I did with 37 is, well, we have the cardioid. That's the 1 minus cosine theta. We have r equals cosine theta. We want something that's common to both the regions. So it's just these kind of pedal looking regions. But I just focused on, okay, if I can just get the area of this pedal region, then I basically can just double it for my area. So I created a zoomed in version of just that one pedal to see if we can find the area there. So start off by finding your intersection. Which 1 minus cosine theta equals cosine theta. I get 2 cosine theta equals 1. So theta is either pi over 3 or 5 pi over 3. But pi over 3 is easier since that's just first quadrant. So here's my strategy. If I can find the area that sweeps from the region that is involving 1 minus cosine theta, I can create an area formula for that region. And I can create an area formula for the region from pi over 3 to the polar 0 on the r equals cosine theta. Remember, anytime we find area, it always has to stem from the polar zero and kind of sweep in a counterclockwise direction. And sometimes it helps, I think, to create table of values so that you kind of know how the graph is moving. So for the cardioid, 1 minus cosine theta, we start here, and we're kind of going this direction, right? But the r equals cosine theta is not starting here, it's starting here. It's moving. So that's why for the 1 minus cosine theta, we can go from 0 to pi over 3. But then for the r equals cosine theta, we go from pi over 3 to pi over 2, because pi over 2 is where it gets back to that polar zero for that cosine theta. So my area formula is 1/2 integral r squared d theta. I added up those two regions, but then in the end, I'm doubling it to handle this portion too. So 38 is a similar strategy. See if you can use what you see with 37 to help you with 38. Show 38. So from 0 to pi over 4 in blue, I'm involving that r equals sine theta to give me half of the region that I need. And then from pi over 4 to pi over 2, I can hit the r equals cosine theta to find the area of that region in red. All right, so your homework over the weekend, page 5 through 10. I also encourage you to start reviewing, practicing for your test on Tuesday. I'll have a health session, a morning health session, 7:30, Monday and Tuesday, going over worksheet 3. We can do some more practice on Monday, but we're gonna spend the first half of class going over 10.3. Okay, so test Tuesday, health sessions Monday and Tuesday, and also send out a reminder of all that on Sunday. Okay. All right, come get your phones.